The answer as shown to be correct does not appear to be correct.
Mm,
I checked the text thoroughly.
it
They
was
are
not
not
there.
discussing about collection of the sample from great depths. They say it can collect relatively undisturbed sample. This is what the lecture material says.
Mhm. Okay, for this will come at the end. First, let me start the lecture for today. Okay. So hello, welcome all. So today is the last session for the subject, the last session for the week 8 lectures. So we'll be discussing about the week 8 lectures, yeah, week 8 lectures, problems, and some of the discussions for the subject subsurface exploration, importance, and techniques involved. So, good evening, everyone. I am Balram Shah. I am the PMRFTA for this course. I am doing my PhD at ICVAR at IIC Bangalore. So, let's start the session. In the week 8th lecture, what we have seen is the dynamic testing of pile. So, before going to the dynamic testing of pile, okay, it's not working again. It's working. Yeah, so before that, I will show you something. Okay. Okay, so in week 8 lectures, what we are going to study is dynamic testing of pile driving. So before that, where do we do the pile foundation? Like what kind of soil and all? When we go for the pile foundation? It's clear. Yeah, it's clear.
When we don't come across uh, good soil at shallow depth, then we go in for deeper levels.
Hmm. Oh no. Can you
If
please say it
we are
again?
expecting rock, etc., at deeper levels,
Ha
when
ha.
we don't get good soil at shallow depth,
Hmm.
then we prefer to go in for pile testing.
Yeah. We should not
We
say it
can get
as good
relatively better
soil.
soil at
Ha.
greater depths. So
Mm.
pile foundation is resorted to.
Yeah, correct. So whenever we see soft soil or the soil which are having low bearing capacity and all, so and at greater depth we want to do the foundation for bigger structures, then we go for this kind of pile foundation. Okay. Now what happens when we design the pile foundation? We consider some bearing capacity of soil, then what is the strength of the soil and all. But what can happen is during the driving of the pile, uh, because of the pile driving, what can happen, the structure or the strength or the properties of the soil can change, isn't it? So to understand that, while driving the pile also we have to do some kind of test to know whether the properties or the strength or the bearing capacity whatever we have considered in the design of the pile foundation, is it staying intact or not. Okay. So if there is any change, what kind of change or how much amount of change is happening because of the driving of pile. So we'll be discussing about the dynamic testing in pile drive today, and we'll be seeing some of the questions and all. Okay, so as I have discussed that the if the pile is getting driven in the soil, it can cause disturbance, and thus it may change or alter the actual soil structure, the bearing capacity, the whatever properties of the soil, it can be changed. It is possible that it might not change, but it is possible also, right? So this way the actual resistance of the soil that will be offered to the pile load might be different from the one which we have determined from the in situ investigation, like whatever geotechnical investigation what we have covered, like SPTs, CPT, then vein shear test, and whatever test we have studied. So the objective of this dynamic testing is, what are the objectives for the dynamic testing? The objectives for the in situ test or the dynamic testing is to determine the actual stresses that are going to be developed in the as well as soil as well as the pile while driving the pile. Okay, first of all, to determine the actual stress, and then let us say we are having some friction pile or end bearing piles, then what can happen, we have to know the skin friction and the end resistance or the toe resistance in case of what I said, friction piles or end bearing piles, deciding the actual pile capacity, actual pile capacity that is casted in situ. So testing this kind of testing is called high strain dynamic testing or large strain dynamic testing or large strain dynamic testing. So in this, what we are seeing, like let us say when we have to go for this kind of high strain dynamic testing, let us say when the impact load is the amplitude of the load is very high, or let us say there are several horizontal, lateral loads, cyclic load, etc., they are there. So while driving the pile, we have to go for this kind of tests. Okay, and other than that, we have restrike means we have, for understanding the long term performance of the pile, we have to go for restrike tests also. So this kind of tests is being done for 5 to 10% of whatever number of piles are there. Let us say 400 piles are there, so 5 to 10% of 400 number of piles will be used, or in like randomly we'll choose any piles out of the 400 piles, 5 to 10% of those, and that will on that the test will be conducted. So this kind of test is being done on driven piles as well as board piles. Okay, so this kind of test is not done on cast in situ pile. Why? Anyone?
In fact, this board pile may also come in the category of cast in situ piles. When
Yeah,
you do boring, after that we are doing cast in situ piling only.
but in that we have some kind of load or some kind of impact. So wherever we have the we can give the impact, there we go for this kind of high strain dynamic testing. So let us say wherever we don't have any hammer impact, for those kind of piles we don't go for high strain dynamic testing. Okay, so in this tests and all, whatever dynamic testing will be there, we have some sensors called strain sensors and acceleration sensor or acceleration sensors, or we call it accelerometer also. Okay, so there will be some strain sensor, there will be some acceleration sensor, and based on that we'll get all the data and we'll understand whether the properties or the structures are changing or not. So basically this so what is the beauty of the test, like, because anyway we are driving the piles, so while driving the piles only we'll use the sensors and then we'll get the whatever information we need. The main advantage of this test is like we don't have to go for other piles and like test on some other piles other than the piles that we need in the construction. Okay, so mostly these sensors will be attached diagonally opposite to each other. So but before that we'll go to some questions. Let us do some questions. अरे, just let you take over. अरे, hmm. So question is, the purpose of large strain dynamic tests is to validate the pile cross section and length as per the design requirements, then detect any cracks present in the piles, determine the stresses developing during the hammer and resistance offered by the pile, and all of the above. Okay, so we have to go into this. Anyone?
C will be the answer.
High strain dynamic testing. Determine the stresses developing during hammer and resistance offered by the pile. Yeah, correct. So why it's not working, man? Hmm. What is happening today? Okay, let me do it here. Now it should work. Yeah. Okay. You can see my screen. Is it?
Yes, yes.
Yes, sir.
Okay, okay. Sorry for the trouble that is happening. I don't know what is happening. Okay, so the purpose of the high strain dynamic tests is to determine the stresses developing during the hammer and resistor offered by the pile. Okay, so we'll be coming into this again. Okay, we have not come into this. Okay, first I will explain and then I will come into this. Okay, yeah, where were we? So what happens in this testing is, at what we'll do, we'll hammer or we'll give some impact load, and to drive the pile in the soil, as I said, there will be sensors, the strain sensors, the acceleration sensor or the accelerometer. So the sensors will detect each impact in analog format, and then it will be transferred to the unit where the digital processing will be there, or this analog signals will be converted to digital signals to better understand the data or interpret the data properly. So this test is known as, so what we are discussing right now is the high strain dynamic testing. So one of those tests is, अरे ये क्या हुआ है, अरे आज ही जो होना है हो रहा है, या इट्स वर्किंग, नो वाई, इट्स वर्किंग, ओके. So the test is known as PDA test, or pile driving analyzer test. So in this, what we will do in pile driving test, we'll know what is the dimension of the pile, like what is the cross section of the pile, what is the length of the pile. Then also will also know the impact, no, not the impact, the hammers, whatever details are there, like what is the weight, total weight of the hammer, what type of hammer it is, then from how much height the this hammer will be dropped, then what is the hammer efficiency. Okay, so what all we need, the inputs that we require for this tests are, as I said, pile dimensions we need, then we need hammer details in the sense what all I said, the weight of the hammer, the type of the hammer, then hammer efficiency, the drop height of the hammer and all. Then we also need the subsoil information and all. This kind of inputs we need, and after doing the test, what all we'll get, we'll get the how much is the pile load carrying capacity, whether and that is matching with the design carrying capacity that we have got. Then as I said, here also I said actual stresses. So the stresses that is developing in the pile while we are driving, it can be like compression or tension, whatever. Then other than that, if is there any strain, what I meant is any kind of displacement if there, if while driving, whether the pile is getting having any kind of displacement. So any displacement of pile while driving, then uh, how many number of blows are required to drive the pile. Otherwise what will happen, let us say if we are giving more number of blows, so what will happen, the soil below the pile can be crushed. Okay, so we need to know that at how much number of blows of the hammer we have to stop. So blow counts to terminate the driving, then what is the minimum depth of installation and all, minimum depth of installation. Okay, so in this test, as I said, what we have two sensors. First of all, we don't have to go for any other piles and all, and the piles that we have, 5 to 10% of those. We'll randomly choose any 5 to 10% of the piles and we'll do the test in that only. So what will happen, there will be before that what I was discussing was strain sensors and acceleration sensors. So what is the purpose of strain sensors? Purpose of strain sensor is mainly to know the resistance to the impact load. And what is the purpose of acceleration sensor? The main purpose of the acceleration sensor is to know the pro propagation particle velocity. Oh, sorry. Propagation particle velocity against the impact or the hammer impact through the pile material. Okay, for the through pile material. So mainly the acceleration sensor and the strain sensors are used for this. So how we are getting this in this sensors, how will they detect? We'll do the hammer impact. So what will happen, as we have studied in the some of the geophysical survey also, isn't it, there will be some sonic waves and all. So like that, if we are giving some hammer impact, what will happen, waves will travel in somewhere I mentioned the compression and tension forces will be there. So wave propagation will be there, and that will be interpreting, and depending upon the nature of the resistance provided to the pile, sensor will detect whether those are direct waves or the reflected waves. Anyway, in the seismic survey and all, we have discussed what is direct wave and reflected waves. So that way these sensors will determine, not determine, will see what is the collective uh, resistance offered by the soil, piles, then if there is any skin friction, toe resistance, if there are some other mediums of soil, like that. Okay, so for this, whatever impact load will be there, we'll understand from that what kind of waves are there, and based on that we have different solutions. So in this test, what will happen, let us say we have this pile head, this is the pile head, and this is the pile. Okay, this is the pile, is some kind of pile I am making. So this is the pile. So here we will have the strain sensors, acceleration sensors. Okay, and this side also someone will be, and that side also there will be. So let us say this one is the strain sensor, and this one is the acceleration sensor. Okay, and here the hammer impact will be there. Okay, hammer impact will be there. Okay, and there will be one cushion between the pile head and the impact also. Okay, whatever. So in this, what I said, there will be hammer impact from the top, and then what will happen, we have the acceleration sensor and strain sensor. Basically this is kept at 1.5D from the pile head. So what will happen when the hammer impact is given, so what will happen, waves will be traveling like this, isn't it? So waves will be traveling in this directions. Okay, let us say that the total length of the pile is L. So the waves will be traveling with a velocity, let us say c, and after traveling till the bottom, what will happen, it will get reflected back, isn't it? And again it will travel L distance, and then it will be sensed at the acceleration sensor, and whatever sensors we have on that, it will be sensed, and again it will come back, again it will go, and what will happen, the amplitude of the wave will be decreasing slowly. Okay, so from the Timoshenko et al in 1970s, they have given this velocity of particle motion against the impact load is given as Vt is equals to C by Ea into f of t. What is C? As I said, C is what? C is the propagation velocity through the medium, and E is the dynamic modulus elasticity, or Young's modulus, as we say, Young's modulus. And this, if you want this C can be determined as E by rho, where rho is the mass density of the soil, mass density of whatever medium we have. So mass density of the medium, A is the cross section area of the pile, and Ft is the impact load, impact load. Okay, and whenever the load is, or whenever the load is considered in the downward direction, then we consider it as positive, and when it is in the upward direction, then we consider it as negative. So in case of, let us say, in case of, I'm not going into the derivation, in case of freestanding pile, what we get is Vt equals C by Ea into f of t. So what is happening here? First the wave will be traveling downwards, then again it will get reflected back, again it will be sensed into the sensors, again it will come back, again it will go, like that it will happen. So it will be like Ft, the first, this Ft whatever you are seeing is the direct impact load that we are getting. That time only it will be sensed at the sensors. Then what will happen? It will come down and it will go back. So there will be first reflection, and that will be 2f into t minus 2l by c. Why 2l by c? 2l by c is the time taken by the wave to travel from the pile head to the bottom, and then again reflect back and sensed at the sensor. So that will be the time required for the waves, or the first reflection, if we say. This will be the first reflection. Then again what will happen? Then again it will come and again it will go up. So it will be like 2f into t minus 4l by c, because now it is the second reflection. This means what? It has traveled once down, again went up, again it came down, again it went up, like that. So this will be my second reflection. Then what will be? Then it will be 2f into sorry, not into, 2f of t minus 6l by c, like that it will be. Okay, but what is seen is, while doing these experiments and all, whatever reflections that are there after the second reflection, those are very feeble, like very weak waves will be there. So whatever after the second reflection will be there, it will be considered as negligible. So after that it is considered as 0. Okay, so what I said is, signals after the second reflection will be very weak to be sensed, or detected, whatever you say. Okay, so did you get what is happening in this pile driving analyzer test?
Yes, please. Yes.
Yeah, so this one was the case for freestanding pile. Now let us say if there is some some friction pile or end bearing pile, then what will happen? In case of friction pile or end bearing pile, what will happen? Again, let us say we have the pile like this. We have pile head here. Here we are having the load. We have sensors here. Okay, now what can happen? The medium in between can give some skin friction. So let us say we have some medium here, some soil type, which is giving resistance. So what will happen? When the impact is coming from the pile head, it will come down, as it was happening in the last one. Wave is coming like this. Now what will happen at this point? Let us say in the midpoint we are considering impact load is coming. In that, what will happen? Some part will go down and some part will again reflect back, because we have some different medium and that is providing some resistance to the wave. So what will happen? Some of the waves will be traveling back or reflected back again, and some portions of the wave will go down, and again it will go down. So some part, sorry. Hmm. So some part will be traveling downwards and some part will get reflected back and again go upwards. Okay, so let us say the distance from here to here is x, and as we have considered last time, the length of the pile is L. Okay, so again the wave that is traveling downwards, this wave which is traveling downwards, it will go till the end and again it will reflect back and it will go like wave again. Okay, so let us say like this I have showed with one soil type. There can be several different layers which is giving resistance to the pile shaft, and so there can be different number of layers which is offering resistance. So what will happen? It will offer resistance from whatever we have considered intermediate depth, x. Okay, so what will happen after the first reflection that they are getting is after at x by c time, isn't it? So this resistance will have two components. One will be the upward traveling compression wave, and the second component, what is there? What is the second component? In the figure you see one is going upward and that is the compression wave, and the other one is the downward traveling tensile wave. Okay, so let us give this number. So for the first component, what will be my V? It will be like C by EA into R of T. Okay, and there will be one half will be multiplied. Why this half is getting multiplied? Because half is getting multiplied because half of the wave will travel upward while half will travel downwards. That's why we are having multiplying half. And the second component, it will be like the time will be 2L L L, and this will be so 2L minus, let us say there are for here it is 2L minus x by c will be my time. Okay, now let us say we have different layers. Okay, let us say we have I number of layers, I number of soil layers. Then for the second component, the time will be 2L minus xi by c. Okay, so the velocity can be written as, so this first one anyway, the upward traveling compression wave is easy, but here what is happening? First one is traveling downwards, the tensile wave, and again that is getting reflected back. Again it will come back and it will do like this. So the net velocity, so if we consider the net velocity in the sense, what net velocity is like the upward and downward components whatever is there. So the total velocity, not we can't say total because it is called as net. So it is the net velocity that is happening because of the upward and downward components, and it can be written as let us say V net t is equals to the upward component velocity and the velocity component which is for the downward wave. So it will be like, for first one what we have, the this RT. What is this RT? So this RT is the change in particle velocity by upward traveling from resistance. So that resistance is this RT. So this will be the summation of the compression wave velocity directly from the resistance and other waves, that is tensile, which is after a reflection, will travel upward. Whatever upward component is there, we are considering in this upward component. Okay, and the downward component we are considering separately. So it will, one will be upward component, so U is for upward component, and one will be my downward component, D is for downward. Okay, so I'm not going into the detail how we are getting. So what we'll get will be C by EA into F of t due to the impact load directly, plus 2 into summation of J equals to 1 to M F of t into t minus 2J into L divided by C minus summation of I equals to 1 to N into Ri of L t minus 2xi by C plus summation J equals to 1 to M L t minus this much of big like expression you don't have to remember and all, just for the writing purpose I'm writing. To M L into this also I'm writing 2J L by C. Okay, whatever. So this, where this M is the number of, how many number of blows we are giving, or number of the impacts that we are having, and N is the number of layers, whatever number of intermediate layers which are providing the resistance. So that will be there. Okay, so from here what we can get, we are having net velocity. So let us say we are having the net velocity and whatever impact force we are giving, then from that also we can get the resistance. Okay, so we can get the let us say we are having, we are knowing the velocity values and recording phase, because for like okay, we are having the ft value and vt value, let us say. Okay, these are known. So from this, from the equations we can get easily the resistance that is offered by the soil, or offered by the pile against the hammer impact. We are having whatever hammer impact is there, we know the impact load, how much impact load we are giving, and we know the velocity. Then from there we can calculate what is the resistance that is offered by the pile, offered by pile against the impact. Okay, so this was what we have in the high strain dynamic testing or pile driving test. Okay, so now we'll move to this question. Okay, so now the question is, in case of freestanding pile, the signal after dash reflection will be very weak to be considered in recording. Okay, so your options are first, second, fifth, and none of the above. Simple.
B will be the answer.
Yeah, second reflection. So after what we have seen, that after the second reflection the signals are very weak. So in case of freestanding pile, the signal after the second reflection will be very weak. Okay, next question is, total of total 40 number of piles are installed at a particular site. The minimum number of piles that will be required to be tested by dynamic pile test is dash. What it will be?
2 to 4.
2 to
A.
4.
4.
And how you are saying that?
5 to 10% is the guideline.
Yeah, correct. So the guidelines are like 5 to 10% of the total number of piles will consider as the minimum number of piles. So 5 to 10% of 40 will be 2 to 4. So the correct answer will be A. At least 2 to 4 number of piles we need to have the dynamic pile testing. Next is pile driver analyzer test is a high strain dynamic test for pile, low strain dynamic test for pile, intermediate strain dynamic testing for pile, or none of the above.
Option A.
Correct. So pile driver analyzer test. We have seen all this. Next is strain sensor and acceleration sensors in dynamic pile testing are used for measuring the impact force and propagation velocity of particle respectively, force and velocity of wave respectively, propagation velocity of particle. What?
D. All of the above.
Uh,
Option A.
uh, it's like strain sensors and acceleration sensors. Can strain sensors measure the propagation velocity? No, right. So all of the above will not be the answer. The correct answer will be impact force and the propagation velocity of particle, because you see strain sensors are for impact force and acceleration sensors are mainly for the propagation velocity of the particle. Okay, so the correct answer will be A. Next is in case of skin friction offered by an intermediate layer along the pile shaft at a particular distance from the pile head, the nature of upward traveling and the downward traveling resistance waves will be respectively in case of skin friction pile. Okay, let us say as last just now we have discussed. So in case of skin friction, upward traveling will be what kind and downward traveling will be what kind?
Option B.
Option B, correct. Yeah. So upward traveling will be compression, compression wave, and the downward traveling will be tensile wave. So correct will be B. Yeah, correct. Next is velocity of particle motion against impact load through a pile Vt as per Timoshenko et al. Is given. Like given is C is the propagation velocity through pile medium, E is the Young's modulus, A is the cross section area of the pile, Ft is the force. What will be the answer?
B.
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 B, yeah, correct. C by Ea into F of t. Just now we have seen. So the correct answer will be B. That is C by Ea into F of t. Okay. Next question is during dynamic pile testing, at what depth along the length of the pile should be the sensors be installed? Should the sensors be installed? Diameter is given as 1 meter and the length of the pile is given as 10 meter.
D will be the answer. 1.5 times the diameter.
Yeah, correct. So what we have seen during the dynamic pile testing, the sensors, whatever sensors we need to install, it should be installed at 1.5 D from the pile head. So the diameter of the pile is given as 1 meter, so it will be 1.5 into D, that is 1 meter. 1.5 into 1 is 1.5 meter. Okay, so the correct answer will be D. Okay. Okay. So the next question is, which of the following are the examples of low strain dynamic testing in piles? Okay, now first we'll discuss what is this low strain dynamic testings and all, and then again we'll come back to this questions. Okay, so now what we'll be talking about will be the low strain dynamic testing. Okay, low strain dynamic testing. Okay, before that I will show you one video, because whatever high strain dynamic testing with what we have seen, no pile driving analyzer, so that we'll see in the video, you'll understand better. Okay, wait. mm, okay, okay, first I have to, yeah. Can you see the screen?
Yes, please.
Okay, now why it is not coming? Yeah, it's coming.
Dynamic load testing of drilled shafts. On a construction
Wait,
site in a
it is
downtown
not
area,
showing.
drilled shafts have been constructed, but no superstructure is in place. The bearing capacity of the drilled shafts will be evaluated by a high strain dynamic load test. A
Wait.
large drop weight is So see, there are number of piles, and now they are putting the, this will be our impact load, this red thing that you are seeing. See, now it is giving force. This is arranged like this. First, the how much amount of impact load will be seeing, will know that. And now they are putting the sensors. See, so like this way it will be bolted, the sensors will be bolted like this, the strain sensors and the acceleration sensors, and from that we'll get the, okay, now see the hammer impact will be there. And like that we'll get this kind of curves, the waves that we are getting, we can get that. Okay. So see here, okay, see here the waves are traveling and we are getting the data like this. So the waves are traveling, we are getting the data like this in the, that pile driving analyzer will be there, that box that you are seeing. So that was the pile driving analyzer, and there we are getting the waves. This one is the acceleration and the strain sensors. Okay, this one is the pile driving analyzer. In this we'll get the data, and then it will be processed in some of the labs, and then we'll get the displacement versus load. So this one, the this curve that you are seeing is for the steady state, not the dynamic testing, the steady testing of the piles. Okay, so that's it. So did you get how we are doing the test, strain high strain dynamic testing?
Yes, yes.
Okay. Srinath, you got it right? What are the sensors, how it is placed and all? Okay. Now I will be going to the Hmm. So now we'll be discussing about the low strain dynamic testing. So what is low strain dynamic testing, or what is the main objective of the low strain dynamic testing? The main objective for the high strain dynamic testing was to determine the stresses that were developing during the hammer, and the resistance that is offered by the pile. Okay. In low strain dynamic testing, the main objective is to understand that whether the pile has the cross section and the length of the pile is correct or not, whatever we have considered as per design. So as per design, what is the length of the pile, that is correct or not, whether the cross section that we have considered during the design, is that correct or not. Other than this, if let us say we have some defect in the pile, defect can be like it is having necking. Okay, we'll write it. So the objective for the low strain dynamic testing are: number one, whether the cross section and okay, I'll write it fully. The cross section and the length of the pile are as per design or not. Okay. And other than that, if there are any defects in the pile cross section, that also we can get through this kind of low strain dynamic testing. So the defects can be necking. You know, let us say we have some, let us say this one is steel rod. Okay, we are giving some tensile load. So what will happen, it will be some kind of this kind of failure will be there. We are giving tensile force to each. So what will happen, it will be like in between it will be like this, and then at the end it will break. So that is kind of necking can be there. Then honeycombing can be there. Honeycombing is what? What is honeycombing? In concrete, you might have seen.
You have
Yeah,
pores in the body of concrete which makes it weak.
yeah, correct. So while let us say this one is the concrete, and some kind of space has been left somewhere while doing the concreting, so that can make the concrete weakened, and that can lead to failure. So that is one kind of defects. That kind of defects can be there in the pile. Then there can be segregation while doing the concreting. Then can be cracks. There can be bulking can be there. Then then what, major voids can be there, arching, etc. And this kind of defects and all we can uh, easily detect from this kind of low strain dynamic testing. So mainly the testing, the tests that commonly done are the sonic logging test, or we say it as cross hole logging test, cross hole sonic logging test. Okay. Or we can go for pile integrity test. Pile integrity test. Okay. So in sonic logging, from the name only you can understand there are some kind of sonic waves, and using those we will do the sonic logging test. So sorry. So in the sonic logging test, what we'll do, mainly it will be like what kind of defects, or if there is any defect in the piles in terms of like in situ method, like this, like sonic logging method will be used to study any possible defects that is there in terms of strength variation in the pile material. So that will like how we'll understand that whether there is defects or not. So if we are knowing the strength for the whole pile, let us say we are having this pile, okay, and we are checking the strength at every point in the length. So what will happen if there are we are seeing that strength is coming constant, but at some point the strength is varying much. So this strength variation, if it is there, then we can understand, okay, that is because of some kind of defect that is present in the piles. Okay, so for that we use this sonic logging test. Plus this sonic logging test we is anyway we are having non-destructive, and if we had the we have the equipment, it will be cheaper than the like it is kind of cheaper test that is possible in almost every pile at the site. We can do this. Okay, so this test will be consisting of detecting the anomaly which are possibly which are the possible defects in terms of acoustic irregularities along the pile length. So what I said, let us say we are having this pile and some kind of what to say, okay, okay, let's say this is the pile, and what is happening, it is coming like this, and there is some kind of defects like this. Defects like what? So there is at this portion there is no concrete. Okay, so this is kind of defect that will that may lead to failure, isn't it? So this kind of defects, they will, from this kind of test we'll understand. What is this test we are discussing is the sonic logging test. So mainly whatever defects we are having, we can understand from the sonic logging test. And what it will consist, let us say waves are traveling and we are knowing the strength at each of the points, and here see, here there are no defect at the top, here there are no defect, here there are no defect, no defect, no defect, no defect, then suddenly there is some defect here. So what will happen, the strength at this portion, at this portion will be different from the top that we are seeing. Again, after this defect, what will happen, whatever strength was there will be normal. Okay, so from that strength variation we can understand whether there is some defects or not. So in this also there will be two probes will be, one will be emitter, another will be receiver. Okay, and that will be lowered in some kind of hollow space, so let us say we have this pile. Okay, okay, wait. Okay, so let us say this is the pile, and what we'll have, okay, we'll have several reinforcements here. So there will be some kind of PVC pipes, the hollow PVC pipes will be there, and in that we'll lower this these two probes, and then we'll check. So I'll change the color. So there will be PVC pipes at 3 inches from the reinforcement. So let us say we have covered this with the PVC pipes. Okay, these blue colored things are the PVC pipes or the hollow pipes, whatever, and black is the reinforcement. This is my pile cross section. Okay, so now so in this hollow tubes or whatever PVC pipes we have, will lower this two probes along the periphery of the reinforcement cage. So now this is the typical this cross section. So now let us say in one of the PVC pipes, this one, we have lowered the emitter, and then what we'll do, in one pile we are having the emitter, in others we'll put the receiver, so that we can understand, okay, we'll know the distance and then we'll understand. So let us say in this we have receiver, let us say receiver 1, receiver 2, receiver 3, receiver 4, receiver 5, receiver 6, receiver 7. Now we know the distance of this, from this to this, from this to this, from this to this, from this to this, we know the distance from each of the PVC pipes to the whichever PVC pipe we have lowered the emitter. Okay, now based on the travel time of the waves, what we'll do, we'll do some hammer impact only, and then the waves will be traveling. Okay, so okay, no, there will be no, wait, okay, there will be no hammer impact in this case of sonic logging test and all. So we'll lower the probe. So what we'll do, first we have the PVC pipes along the periphery of the reinforcement cage. Then what we'll do, first we'll fill that with water. Why we are filling this with water? Anyone?
To ensure good bond with the reinforcement around.
Yes, correct. So then we'll fill the PVC pipes with water. Then both the emitter and receiver will lowered in whichever pipe, PVC pipes, as I have drawn in this figure. No, will lower the emitter in one of the PVC pipes, and in others will lower the receivers. Okay, and then after it reaches the bottom, the emitter will generate some kind of sonic waves, and it will so let us say I'm doing this here. So now here at just at the bottom we have the emitter. Now the sonic logging will propagate. The waves will be propagating like this. Is it? So now this propagation velocity will go to each of the receivers, and the receiver at each of the PVC pipes will detect the waves. Okay, so some of the waves will be detected by the receivers in all whatever other tubes in which we have lowered the receiver. It will detect the waves. Now based on the time of arrival, like see, if the distance is more, the travel time of the waves will be more. Based on it will also depend on the whatever material we have in the pile. But mostly, like if it is same materials is there, so mostly what will happen, if the distance is more, the travel time for the waves will be more. So based on the travel time and the distance between the emitter and the receiver, the sonic wave velocity will be determined. Sonic wave velocity will be determined at test depth. Now what we'll do, we'll again pull it, like for each of the depth we'll do that test. So we'll pull out the probe for at every distance. Let us say in this, you see these are the piles, not the piles, the PVC pipes. So now we are here. Now it will pull again and it will go upstairs up like this at every point in the pipes. Will do the test. Okay, it is like we are not doing anything. It will, the sonic logging board is the digital thing, it is only doing. So we just have to pull out the probe and then it will detect. Okay, so what we'll do, we'll repeat the test at various depths along the pile length, and for each of those sonic wave velocity, however we have seen at the bottom of the pile, like that only sonic wave velocity will be determined. And now from this sonic logging profile, what is sonic logging profile? Sonic logging profile. So this can be the plot between the sonic wave velocity versus the depth. Now at every depth what we have the sonic wave velocity. This we can do for travel time versus depth also. Okay, now we have the sonic logging profile. So that will comment on what kind of concrete is there. I mean, what quality, and the quality of the concrete is good or not at every depth of the pile. Okay, so now as I said, this can be travel time versus depth also, because from there also we can understand. So this can be travel time versus depth. So if the travel time is more, like we have delay in the travel time, so from that what we can understand, the quality of the concrete is changing. Okay, so mostly the test setup for this sonic logging profile will be given by ASTM D6760. Okay, now we'll have this so what we are getting is the sonic logging profile, and from there we can understand the quality of the concrete, whether there are any defect or not. So if good quality concrete is there, then we know that it will be somewhere near to the sonic wave velocity will be somewhere near to 3700 meter per second. Okay, so for water, if you are doing, it will be 1500 meter per second, and for air it will be 300 meter per second. So anyway, before also in this seismic reflection survey and refraction survey and all, what we know that, let us say for air, so for air what will happen, the velocity will be the least. Again, if we go to vacuum, then it will be much lesser velocity will be there, the wave velocity. Okay, so there are several guidelines. So what we do, the concrete, because we are putting PVC pipes in the concrete, so we should remember, or we should remember that the bond between the concrete and the PVC pipes is there. So along the periphery of the PVC pipes, what should be there, the bond between the PVC pipe and the concrete should be strong enough, so that between the two, between the concrete and between the PVC pipe, it is having strong bond. Okay, so sometimes what we do, we like roughen the PVC pipe, and then we put that PVC pipe, and then we do the concreting, so that it has it have some proper bond, it will improve the bond of the tube with the concrete, isn't it? And other than that, then there are several other guidelines, like as I said, there should be a minimum cover of 3 inch should be provided from the tubes along the reinforcement cage. Then minimum 1 tube per foot should be purely vertical, because if it is not vertical, if we are having some, okay, you can see why different. If it is not properly vertical, if it is like this, then the distance will be changing, and based on that the travel time and the sonic wave velocity will be different. Okay, so all the tubes must be parallel to each other. So, okay, parallel to each other means what, if one pile is like this, and the other pile should also be like this. I mean, it should not be in one line, it can be like, okay, I'll show here. So see this, the pile cross section, all the piles that blue colored, not piles, sorry, the PVC tubes. Okay, the tubes should be parallel. Why it should be parallel? Because if we are changing the inclination a little bit, it can increase the travel time, and it can change the sonic wave velocity. So all the PVC pipes should be in parallel. Okay, so all this R1 to R7 are parallel. Okay, and once concreting is done around the tube, as I said, it should be filled with water to ensure no loosening of bond between the concrete and the tube. Okay, and once the this test is done, the water will remove, and then we'll do the grouting in the PVC pipes, and then we'll leave it for, something is happening, you guys can listen to me, okay, if you are having any
Yes,
problem.
yes.
Okay,
Audible.
no, okay, because it was showing something. Okay, so what I was saying, after the test is done, whatever water we have poured into the PVC pipes, we'll remove that, we'll do the grouting into the PVC pipes, and after some time, like 24 hours or so, curing will be done. And then since testing requires continuous power supply, okay, so the whatever this vehicle input or whatever unit is there, it should be properly ensured that the site is having all the facilities. Okay, and first observation of acoustic velocity should be at the bottom, and we'll pull that, and we'll have simultaneous withdrawal of both the receiver and the emitter, both the probes will pull like that. Okay, so what I meant was, uh, let us say here some guy is standing, and there are several, in one emitter is there. So let us color the emitter with green. So the green colored thing is the emitter wala wire. And which one should I choose? Black. Okay, and the black is for the receivers. So there will be wires, and first it will go at the bottom, will take the reading, and then we'll pull it out like this. Okay, so what will happen, at various depths we are getting the data. Okay. Okay, and what I was saying, so remember, if there are any knots in the cable, it should be removed, because while we are lowering the wires also, we should, like, what people do is, they will hold the wires like this, and then will and the wires will go like this, so that there should not be any knots. Because if there is any knot present in the cable, what can happen, it can lead to some incorrect data. So depending upon the findings, the expert can decide to whether to accept the pile or to reject the pile for further assessment. Okay, so this was kind of sonic logging test. So after the means, so in the unit, what is happening, we will get, okay, we'll get some kind of sonic logging profile. This sonic logging profile I'm drawing here. Okay, so it will be, let us say, depth and sonic wave velocity. I'm saying sonic wave velocity. Okay, it will be in meter per second or feet per second, based on wherever you are doing. So what will happen, let us say here we are doing, so if the strength is proper, so what will happen, for every, for different piles we are doing, for 5-10 piles let us say we are doing, so the variation will be like something like this, strength variation, because it is homogeneous and not, we are considering homogeneous and isotropic. So again it is for one pile, again we went to some other pile and we did the test, again we are getting something like this, again for the third one we are seeing something like this. But in the fourth pile, let us say we are having defect. Okay, so I'll draw that by blue, let us say. So let us say at depth of 5 meter, let us say we are having defect. So what will happen, the strength will be like this, but here we are having defect. So what will happen, there can be some change in the wave pattern, and again it is correct, so it will be like this. Okay, so this change in the sonic wave velocity pattern tells us that there can be some defect here. Okay, so this is the indication of some kind of defect. Okay, because we are considering that the pile length is this much only. Okay, up to this we are doing the test. Pile length is L, let us say. Okay, so based on the so we'll get a one average curve also if you want. Okay, so this one will be 3700 meter per second for concrete here, as we have seen. So as I said, this is also called cross hole sonic logging method or cross hole ultrasonic method. Okay, okay, now we'll move to some questions. Yeah, one more low strength testing is left, pile integrity test, as I said. Okay, that we'll see later. First let us do some questions. Okay, so the question is, which of the following are examples of low strain dynamic testing in piles? Your options are pile driving analyzer test, sonic logging test, pile integrity test, and both B and C.
Option D.
D.
Option D, because sonic logging test and pile integrity test both are the kind of low strain dynamic testing. Okay. Next question is, low strain dynamic testing in piles is done to determine the ultimate load capacity of pile, to check whether the pile cross section and length are as per design requirements, to detect the defects in the pile cross section, or both A and B, both B and C. Sorry,
Option D.
option D,
D.
because we do the low strain dynamic testing for pile cross section, length, and that any kind of defects. Okay, so answer will be D. Next question is, guidelines to perform the sonic logging test can be referred from the first one. Okay, ASTM D670. So the correct answer will be
Option A.
option A. Next is, through which of the following medium will the sonic waves have least velocity?
Air.
Air, correct. And in which it will have the highest velocity?
Concrete.
Concrete or rock, depending on what type of rock we have.
Yeah, correct. It can be in rock also, depending on what kind of rock it is there. Okay. So for this, answer will be air. Next question is, what is the minimal distance between the hammer impact and the acceleration sensor in pile integrity test? Okay, pile integrity test. First, we'll discuss what is pile integrity test, and then we'll come back to this. Okay. Okay, so next test is pile integrity test. Pile integrity test. So this pile integrity test also is done to understand the quality of concrete. Also, other than the quality of concrete, it is also done to know the cross section and length of the pile. Okay. Okay. Okay, so main advantage of pile integrity test over the sonic logging test is we don't have to have any tube or whatever tube we have casted in the piles. So we don't have to have any tubing while casting the concrete as we are doing in the cross section. Sorry, cross hole sonic logging test. So in this, it will be consisting of acceleration sensor, as we have seen in the first dynamic testing. So there will be acceleration sensor, but again we don't have to put the strain sensors in between and then we have to do hammer impact. It is simply the acceleration sensor will be put on the top of the pile, on the pile head, and the hammer impact also it will be very low only, because one person can do the hammer impact, and then based on that we have the acceleration sensor, the wave traveling, and then we'll have this data. Okay, so as I said, the what I said, cross cross hole cross hole sonic logging method means what are the advantage, that no tubing required, no tubing required. Other than that, what I said, that acceleration sensor is required, but only at the pile head. Then from the pile driving analyzer test. Like small hammer impact is required. So as we have seen in the video, that much of load is not required. Simply one person can do the hammering and then we can have the data. So mainly this will be the response in terms of reflected wave. Okay, this will be the response of in terms of the reflected waves. Okay, and that will be recorded and it will be utilized for interpretation. So there are several guidelines for the test setup or the field setup, because there are several kind of piles. We can have square piles, we can have circular piles, then sorry, we can have square piles, then we can have circular piles. Array. Then again we can have spun piles. What is spun piles? Spun piles is kind of hollow piles, so there will be some thickness in between. Yeah, so there can be square piles. So for guidelines for square piles is like what I said, there should be we will put acceleration sensor uh, for all the hammer impact. So let us say we are keeping the acceleration sensor in the middle for the square. So the hammer impact should be somewhat it's like at d by 4. If d is the side of the square, then at d by 4 distance the hammer impact should be there. Okay, so this is for square pile. For circular pile, if the circular pile the diameter is less than 0.6, less than or equals to 0.6 meter, then if sensor is put at the center, then at d by 4, any radial distance, let us say at d by 4 of the distance, the hammer impact should be there. Okay, and if d is greater than, okay, that will come later. And for spun piles, let us say we are putting acceleration sensors like this, then the hammer impact should be at a distance of around 75 to 100 millimeter from the acceleration sensor. 75 to 100 millimeter from the acceleration sensors. And let us say again we have circular piles, but d is greater than 0.6 millimeter, sorry, 0.6 meter, 0.6 meter. Then what we'll do, the hammer impact should be like this. So again, let us say we have acceleration sensor, the hammer impact should be in the middle of the acceleration sensor like this. Okay, and these all are based on GNP of 2004. These are some of the guidelines for each of the piles. Oh, sorry. Okay, guidelines for the field setup. And this plus sign means what? Plus sign means hammer impact, and dot means we have acceleration sensor there. Acceleration sensor. Okay, so what we'll get? We'll get the velocity time history from the acceleration sensor record, and upon the hammer impact, the wave will travel between the pile head and the toe with a velocity which is a function of concrete, the quality of concrete. Again, if there is defect, again that will change. So signature of the reflected wave signature will help in the understanding the medium characteristics. So if the reflected waves is going like this, and again we are having some high change, then we can understand, okay, the medium characteristics is changing. So so in this, if there is a sharp reflection, then that is the indication that there is some impedance contrast. Okay, impedance contrast means there is a change in material of the pile section properties. So what is this impedance? Impedance is a measure of the deep foundation's resistance to motion when subjected to an impact event. So let us say we are having an impact event, so the measure of the okay, I'll write what is impedance. Impedance is a measure of the deep foundations. You might have studied impedance in your electrical and all, whatever. So impedance is a measure of the deep foundation's resistance to motion when it is subjected to an impact event. And this impedance is generally denoted by Z, is given as Z is equals to EA by C, that is rho CA, because we know that C is equals to root over E by A, and if you put like that, then you will get Z is equals to EA by C, or like rho CA. Okay. Yeah. So if the length of the pile is correct, like if this is the correct length of the pile L, then what will happen? Then whatever reflectogram will be there, it will be like at the beginning, at the pile head, we are having acceleration sensor. So just at that time we'll have some reflection, some change, and again after length of L, after getting reflected back, we'll have some kind of change. Okay, so see, in this there is no change in between. So this means what? That pile is perfectly straight and length is complete. Okay, let us say we are having small length. Okay, we have not completed the total length, we are not having anything after that. So then what will happen? The change will be there, and again at some up to what length it is, up there only we'll get the reflected wave. Okay, so again it will go like this. So from this what we'll understand, the length of the pile is less. Okay, so that's why we are getting the reflected wave very fast. Okay, and if there is some change in the cross section, okay, it's going like this, and then we have some change in the cross section. Okay, then what will happen? It will be going like this, reflected back will be like this, and again there will be some reflection here. Okay, so this means what? There is a decrease in cross section at deeper depths. Okay, and if the piles is having some irregular cross section, then what will happen? There will be some kind of other waves. Okay, so this means what? There is some irregular cross section of the pile. Okay, so based on this we'll decide whether to accept the pile, whether to reject the pile. Okay, like that. So limit. So from this what you understood, what are can you tell me what are the limitations of the pile integrity test, where this pile integrity test we can't do something like that? Anyone? So the limitations of the pile integrity test is like this test, as I said, detects the defects based on the change in the impedance. Okay, so if there is small change in impedance, the PIT will not be able to capture it accurately. So that is one of the limitation. Impedance dependency. And again in this what we'll see the collective function of pile cross section as and concrete quality. If there is some change in the concrete quality, there are some defects, plus there are some change in the cross section, then this from the surface what we can see is some changes only. but we can't distinguish that whether this is because of the concrete quality, this is because of the change in the cross section. So that is one of the limitation, that it is a collective function. It is a collective function of pile cross section as well as the concrete quality. Concrete quality. So PIT will not be able to differentiate whether the observed change is due to the concrete quality, or it is because of the change in the cross section. And again, this impedance is also a collective effect of the pile and the soil properties. So it is like it is difficult to identify the reason of change as pile or soil characteristics. Okay, so these are some kind of limitations that are there because in the pile integrity test. So so that defects that we can identify using the pile integrity test can be, there can, if there are some cracks or joints, we can understand. If there is some change in the cross section, we can understand. If there is length decrease or increase, we can understand. If there is major change in the material properties, then also we can understand. Major voids, if it is there, we can understand. But if, let us say, there is gradual change in the material properties, okay, then we can't understand. If the piles are curved, then we can't understand. So these are some kind of uh, defects or things we can't detect from the pile integrity test. Okay. Okay. And again, that's it. Okay. I think I have one video for this also. Let me check. That will be a small video, 1 minute video, I guess. Can you see that?
Yeah,
Yes.
it's visible.
Okay. See, there are several piles, and in this we'll do the testing. Which testing? The pile integrity test. So we'll roughen the pile head, because whatever acceleration sensor we are going to keep is on the pile head. So this is the acceleration sensor that this guy is putting, and he is doing the hammer impact. See, because of the hammer impact, the waves are compression waves are going down and again reflecting back to the pile head, and this reflection will give you some kind of curve like this. And let us say we are having some major defect. See, we are having some defects here. We are having some change in cross section, or you can say some necking is there. So what will happen? See, from here only we'll get one reflection. Again at the toe also it will come as a reflection. So we'll have two reflections. We can see here that, see, we are having a dip in the reflection. So from there we can understand if there is some change in the cross section or some change in the concrete quality or defects is there, and then this is used, these curves will be used to understand what kind of concrete quality and all are there, and then the reports will be made. That's it. And this is the acceleration sensor, whatever. Okay, that's it. Yeah, now we will move to the question. Okay, you can see the screen.
Yes.
Okay, so the question is, what is the minimal distance between the hammer impact and the acceleration sensor in a pile integrity test done on a circular pile with a diameter of 0.8 millimeter? So what will be the answer?
0.2.
And how?
D by 4.
Yeah, correct. So it should be d by 4, that is 0.2 meter. Correct. Next is, pile integrity test cannot be used for curved piles, piles with diameter greater than 2 meter, square piles. Oh, this will be piles. Okay, by mistake I did right, and none of the above.
A. Curved piles.
Yeah, correct. For curved piles, we can't do, because piles with whatever diameter we can go for pile integrity test. For square piles also we can go. So correct answer will be curved piles. Next is in pile integrity test, changes occurring in the impedance is a collective function of which one?
All of the
All
above.
of the
B.
Yeah, correct. So the whatever impedance change is there, that is because of the pile cross section, because of the soil properties, because of the quality of the concrete and all. So the correct answer will be all of the above. Now, as per Turner 1997, defect that can be identified by pile integrity test is major change in material properties, gradual change in material properties, joints, cracks.
This gradual change cannot be detected.
Yeah. Okay. So okay, I read. Sorry. It should be cannot. Okay. Sorry. Okay. So the correct answer will be gradual changes in material properties cannot be detected. So the question should be cannot be identified. Okay. Sorry for that question mistake. So correct answer will be B. Got it? Okay. Next is in a pile integrity test that is performed on a circular pile of diameter 0.4 meter, what would be the minimum distance between the hammer impact and the acceleration sensor in the circular pile?
0.1.
Yeah, again, if the diameter is less than or equal to 0.6 meter, it should be d by 4. So it should be 0.1 millimeter. Correct answer is A. I think that's it. Uh, as a conclusion, if I say what all we have studied, uh, so we have hmm. So as a conclusion in this subject, that is subsurface exploration importance and techniques involved, what all we have studied, that why we should go for subsurface exploration importance, subsurface exploration, what is the need of it, and what are the things we need for doing the subsurface exploration. Then we move to what are the processes that we can do, like what are the methods that we can use to go for the subsurface exploration. So like boring, drilling and all we have studied. Then if while doing the subsurface exploration, we have to also go for all the investigations, like preliminary investigation, detailed investigation. In that, what we have seen, how to handle the legal issues if there are some legal issues can be there, because we have to keep in mind that okay, if there are some adjoining structures are there, that should not also that should not have any effect because of our construction. So all that should be considered in the investigation. There should be detailed investigation. Before that, we have to have preliminary investigation. So for this, we move to what all methods we can apply in the subsurface exploration. What all methods we can apply? We can go for geotechnical investigation, we can go for geophysical investigations and all. So in the module 2, what we have seen, in the module 2 we have studied about the geotechnical investigations. So in the geotechnical investigation only we have seen the test pit, trial pits, whatever, boring, drilling, what kind of augers and all we have seen na. So those things we have studied. Then what are samples, like what kind of samples are there, disturbed sample, representative samples, non-representative sample, that is undisturbed samples. Then how the groundwater table impacts, what is the importance of knowing the groundwater table, and the saturation of the soil and all. Then sampling of the soil, or even if we are having rocks below the surface at the subsurface, how to do the rock sampling, how to do the drilling. Then what are the methods we have gone, the geotechnical investigation methods were vein shear test, then standard penetration test, cone penetration test, dilatometer test, pressure meter test, and all. So from there, how what is the basic physical physics behind this test, how we are taking the field observations, and after taking the field observation, how we are interpreting it. Okay, then we move to the geophysical investigation. In the geophysical investigation, we have seen that many non-destructive tests we can apply. What is the advantages of the geophysical test on upon that of geotechnical test? What are the limitations of the geophysical test? In this, we have we have seen the seismic reflection survey, seismic refraction survey, other surveys like electrical resistivity survey, then magnetic survey, gravity surveys, and so on. And then we move to the offshore investigation. And as I said, in 2 to 4 lectures, the offshore investigations is very less time because it is a almost a very vast subject. And so even then we studied the offshore investigation, what is offshore environment, why should we go for offshore environment, like offshore investigations, what are the methods that we apply for the geotechnical investigation, geophysical investigation, like bathymetry, then echo sounding, sonar, and all we have seen. How we are getting the samples, what kind of samplers we are using, then the platforms that are there near the offshore environment, jack-up platform, jacket platforms, and all. And today it was the last session for the lectures, and in this we have discussed about the dynamic testing of pile, the low strain dynamic testing, the high strain dynamic testing, then this whatever test we have seen, pile driving analyzer test, then pile integrity test, sonic logging test, what is the advantages of this kind of tests and all. Okay, so I hope you guys understood whatever I taught. Like I enjoyed a lot from this sessions and all. I hope you guys also enjoyed. And if you have
Well
any
present.
you have
Very
any
nice.
doubt and all, you can ask. About the question that you are saying now. Okay, let me check once. Question number 7 you are saying, na? What is the primary advantage of using a box core sampler? But the thing you are saying, no, undisturbed sediment cores are there. So mostly in the box core sampler, we have kind of less disturbed soil than the other samplers. So yeah, I understand that this was not mentioned, but this undisturbed sediments we can't go for it. You can collect sediment sample from. Okay, so the correct answer for this will be the C only, but you are getting my point, because in the box core, what I said in the last lecture on last session was, in the box samplers, whatever the samples we are obtaining are relatively less disturbed than the grab box samples or whatever, and that so that it can be used for the determination of the index properties like density, moisture content, also the strength properties from the lab investigations. Okay, so this greater depth is can go box core sampler. So the correct answer will be C only. Okay.
Right.
Anything other than this? And even if you are having any doubts and all, you can like let me know in the that question session is there, no? There. Here. Here you can just post whatever doubts you have. And if you need some kind of like practice session for all the weeks, that also I can arrange. When is the exam? Today is 18, 19, 20, 21, 22, 23, 24. Oh, so it can't be arranged, I guess. Okay, even if you are having any doubts and all, let me know. If it is like more than 5 6 people's want someone extra class or something, I can go for it. Okay. Any other doubt? you guys are
Okay,
having.
well presented. Well
Thank you
presented.
so much. Thank you so much. I enjoyed a lot from these sessions and all. I hope you guys also enjoyed, because I wanted this to be interaction, so I put GIFs, videos, and all so that you can understand the tests better. Okay, so no doubts. Then we'll close the session. I'll stop the recording.
Okay, thank